The morning of August 19th, 1942, broke grey and cold over Deep Beach in France. By nightfall, 97 Canadian soldiers lay dead in the sand and surf. 6 hours of combat had delivered a message so brutal it would reshape the entire strategy for winning the war. The blood, the bodies, the impossible arithmetic of modern warfare, these details carved themselves into every Allied commander's thoughts. You cannot simply storm a fortified port and expect to win. Yet the Allies faced a crushing reality. Without ports, everything falls apart. 200,000 men would perish on Normandy's beaches unless someone found an answer to a problem that seemed to have none. The challenge was maddening in its simplicity. The solution would prove impossible in its scope. 2 engineers stepped forward, men whose names the establishment spoke with equal measures of respect and doubt. First came Hughes, a methodical Welsh concrete expert who believed in overwhelming force. His thinking centered on massive blocks, 7,000 tons each, that would somehow have to float across 100 miles of open ocean. The English Channel itself. The idea sounded absurd to almost everyone who heard it. Then there was Alan Beckett. A Royal Engineer who had survived Dunkirk, he carried an entirely different vision. Where Hughes saw concrete as something to be wielded like a weapon, Beckett imagined it dancing with the sea's rhythms rather than fighting against them. He wanted structures that could move, flex and breathe with the waves themselves. Royal Navy officers scoffed at both men. Concrete doesn't float, it sinks. That was naval wisdom earned through centuries of experience. American planners dismissed the whole concept as fanciful British dreaming. Even Churchill's own advisors whispered their concerns in private. The physics didn't work. The mathematics didn't support it. No one had ever done anything like this before. But September 1943 would change everything. The Scottish waters off the coast became their proving ground. When Atlantic storms rolled in with winds gusting at 40 knots and waves climbing to 15 feet, the true test began. That brutal night revealed which design possessed the vision to survive, which engineer understood the marriage of concrete and sea well enough to reshape modern warfare itself. What happened during Operation Jubilee in August haunted everyone involved. Canadian Rangers had charged into German machine gun fire that dawn, their bodies twisted grotesquely in the surf by evening. The blood mixed with salt water in patterns that seemed almost deliberately cruel, as if the channel itself had conspired with the enemy. For 3 days, the bodies washed ashore. 907 men died in those 6 hours. The operation's promise, capture the port quickly, hold it for a day, withdraw with intelligence and honor, dissolved into one of the war's harshest lessons. Fortified ports cannot be taken by frontal assault. In the corridors of Whitehall, where the fate of nations was decided, this single fact created an equation that threatened everything. Every gallon of fuel, every ammunition round, every replacement tank needed to sustain an invasion force required a functioning port. The Germans understood this logistics equation as clearly as the Allies did. They had spent 2 years fortifying every harbor from Norway to Spain. Concrete gun emplacements, steel obstacles, killing fields positioned with surgical precision. Hitler's Atlantic Wall served one purpose: make the ports impenetrable and the invasion starves on the beaches. The mathematics were brutal and unforgiving. 2 million Allied soldiers would need to cross the Channel for Operation Overlord to succeed. Those men would require 5,000 tons of supplies every single day. Ammunition, food, medical supplies, vehicles, fuel. Without a deep-water port, supplies would trickle in by landing craft across exposed beaches, vulnerable to weather, tides, and German guns. The War Office calculated the numbers repeatedly. The answer never changed. Without ports, D-Day was suicide. Winston Churchill grasped the problem with characteristic clarity, though his solution sounded like the rambling of a man who had enjoyed far too many brandies and cigars late into the evening. On May 30th, 1942, barely 5 weeks after the Dieppe disaster, a memo arrived at the Admiralty bearing the Prime Minister's unmistakable handwriting. It contained 3 words that would either revolutionize the invasion or confirm that Britain's wartime leader had finally lost touch with reality: piers for use on beaches. 3 simple words. They carried within them an audacious concept of breathtaking simplicity. If you cannot capture a port, build your own. Not on land, where German artillery commanded every harbour, but floating on the water. Construct massive concrete harbours in British shipyards, tow them across 100 miles of open sea, then sink them precisely off the Normandy coast to create artificial anchorages that could accommodate the largest cargo vessels. The engineering establishment's reaction mixed fascination with deep skepticism. Fascinating because it solved what seemed unsolvable. Skeptical because it violated every principle of marine architecture anyone had ever learned. 3 engineers presented competing visions for Churchill's impossible dream. The first offered canvas roadways that could unfold like carpets across the water, promising rapid deployment but raising troubling questions about whether canvas could support 40-ton Churchill tanks moving at combat speed. The second proposal came from Hughes, 40 years old, a Welsh civil engineer whose childhood sailing trips along the Conway coast had taught him to respect concrete as something alive and negotiable, capable of conversing with wind and wave. Hughes carried the credibility of 15 years working alongside Owen Williams, the revolutionary architect whose concrete towers had defined Wembley Stadium and whose elegant bridge spans had transformed the landscape. His vision remained uncompromising. Massive concrete caissons he called hippos, each weighing 6,000 tons, linked by rigid steel roadways dubbed crocodiles. Where his competitor offered flexibility, Hughes proposed absolute strength. Immovable concrete foundations that would turn sections of the English Channel into extensions of Britain itself. From within the Royal Engineers emerged Alan Beckett, just 29 years old, a man who had spent 3 years contemplating problems the textbooks insisted were impossible. Unlike Hughes, whose reputation rested on architectural monuments, Beckett was a working-class pragmatist who had started the war digging defensive trenches at Dunkirk. He had learned to distrust any solution built purely on static defense. His floating roadways would rest on concrete pontoons he called beetles, connected by flexible joints that could bend without breaking as waves lifted different sections. Most revolutionary of all were his kite anchors, streamlined concrete weights that used hydrodynamic principles to generate 30 tons of holding power from devices weighing 1/10 that mass. By September 1943, the skepticism had crystallized into a single, devastating critique that echoed through every military club and engineering society gathering in London. Concrete doesn't float. Royal Navy officers, men whose careers had been built on understanding what the sea permitted and what it rejected, dismissed the entire enterprise as British eccentricity gone mad. American planners, still wounded by their own failures at Kasserine Pass, viewed Churchill's floating harbours as evidence that their allies preferred technological theatre to practical warfare. Even within Churchill's own government, doubt spread like infection. The physics seemed to mock common sense itself. 6,000-ton concrete blocks would somehow float 100 miles across waters that regularly destroyed ships built specifically for such journeys. They would then sink precisely into position. They would then survive Atlantic storms while supporting crushing loads from vehicles and cargo. Forces that would make the structures flex and twist in ways concrete was never designed to endure. The whispered conversations in Whitehall grew sharper as autumn approached. 3 competing designs, each consuming millions of pounds and hundreds of thousands of workers, all gambling on the premise that 2 centuries of naval architecture had somehow overlooked an obvious solution. Could Hughes's concrete caissons actually survive being towed across the Channel without shattering? Could Beckett's flexible system hold together under the weight of Sherman tanks racing to reinforce beachheads under German fire? The answer would come in the violent waters off Garliston, Scotland, where Atlantic gales would test each design against forces that had destroyed ships since men first ventured to sea. The 2 men would determine D-Day's fate, yet they emerged from entirely different worlds. Hughes carried himself with the methodical precision of a Welsh chapel elder, his conversations punctuated by long silences as he visualized stress patterns and load distributions in structures existing only in his mind. At 40, he had spent 15 years as Owen Williams's protégé, learning to perceive concrete not as dead matter, but as living material, something that breathed with temperature changes, flexed under loads in ways demanding intimate understanding rather than mere calculation. His reputation rested on architectural marvels that married engineering boldness with aesthetic grace. Wembley's soaring concrete towers, the Dorman Long Bridge's elegant spans, structures built to endure for generations because Hughes understood how to make concrete negotiate with forces rather than simply resist them. Beckett represented everything the engineering establishment distrusted about wartime innovation. A working-class Londoner who had earned his commission through battlefield promotion rather than university credentials, he approached problems with the hands-on pragmatism of someone who had learned engineering by fixing things that broke under combat stress. Where Hughes spoke in terms of architectural permanence, Beckett thought in terms of survival. His mind had been shaped by 3 years of watching German bombs destroy structures designed to last forever, teaching him that flexibility often mattered more than strength when forces were trying to kill you. His spare hours at Erath Yacht Club involved not leisurely sailing, but systematic experimentation. Testing anchor designs in tidal mud, studying how small boats rose and fell with storm swells without breaking apart. The technical challenge that brought these men together defied every principle of marine construction that had guided naval architects since ships first put to sea. Beckett's revolutionary insight had crystallized during a weekend at Erath, watching his sailing drone's kite rise and fall with wind gusts, remaining perfectly controlled by its anchor system. Traditional engineering wisdom demanded that bridges be rigid, that foundations be immovable, that any structure carrying heavy loads resist movement through mass and strength. But watching the kite dance with air currents rather than fight them, Beckett realized his floating roadways must embrace motion rather than resist it. Rising and falling with 15-foot tides, flexing with wave action, supporting 40-ton Churchill tanks moving at 15 miles per hour, while the entire structure twisted and pitched like something alive. The mathematics of this flexibility challenged everything he had learned about concrete construction. The Whale roadways would stretch across 80 feet between floating pontoons, with each section engineered to handle the most concentrated loads, stresses that would shatter traditional rigid structures instantly. Beckett's innovation centered on what he termed torsional flexibility, joints designed to move independently around their lengthwise axis, rising and falling with the rhythm of the waves while remaining well within the safety limits provided by steel reinforcement embedded throughout the concrete. Spherical bearings at every connection point offered movement in all directions, keeping the roadway surface level enough for vehicles to race across and reinforce the embattled positions beyond. Hughes pursued an entirely different path, favoring engineering that relied on overwhelming structural force instead of flexible adaptation. His Hippo caissons represented concrete engineering taken to monumental extremes, each one stretching 200 feet long and 60 feet high, with walls measuring 2 feet thick and interiors divided into 18 individual compartments. When finished, these massive floating fortresses would weigh 7,700 tons, heavier than many warships themselves, intended to settle on the seafloor like artificial islands capable of enduring any storm through sheer immovable weight and resistance. His crocodile bridges would connect between the Hippos using rigid steel frameworks, creating straight highway passages strong enough to support the heaviest Allied equipment without any bending or vibration whatsoever. The difference in their anchor systems revealed how fundamentally opposed their thinking truly was. Hughes counted on his Hippos to achieve stability through pure mass. Once positioned and sunk, they would hold firm through gravitational pull and friction between structure and seafloor. Beckett's kite anchors represented a breakthrough in holding systems, harnessing hydrodynamic principles to magnify their effective weight through water pressure and streamlined design. Each anchor weighed merely 3 tons, yet generated 30 tons of holding capacity by utilizing current flow to force its angled surfaces downward against the sea floor, producing exponentially greater resistance compared to conventional deadweight anchors. In September 1943, both systems arrived at Garliston Bay along Scotland's southwestern coast, where fierce Atlantic weather would test their opposing philosophies to their limits. Hughes's prototype reached the site following 2 months of construction at a Welsh facility where 1,000 workers had shaped what resembled less a harbour component than a concrete cathedral designed to survive apocalypse itself. The hippo caissons rose from Welsh soil like ancient monuments reborn, their massive walls reinforced with steel mesh and their compartments fitted with pumping systems capable of flooding or draining individual sections to adjust buoyancy with remarkable precision. Beckett's whale sections appeared almost delicate alongside them. Their 80-foot spans rode pontoons that moved with wave motion rather than resisting it. The flexible connections Beckett had engineered looked impossibly fragile to those accustomed to Hughes's monumental approach. Spherical joints permitting three-dimensional movement, torsion boxes that could bend without breaking, anchor systems that seemed to defy basic physics by producing enormous holding power from comparatively small masses. Early trials displayed the strengths and vulnerabilities of each method with stark clarity. Hughes's rigid system performed beautifully under heavy loads during calm conditions. The crocodile bridges provided surfaces smooth enough that tanks could cross between hippos at maximum speed without vibration or any bending. Beckett's earlier canvas rolling roadway proved inadequate almost immediately. Its 7-ton maximum capacity meant Churchill tanks would simply tear through the canvas material into the water below, destroying any vehicle and likely drowning its crew. Yet Beckett's flexible system raised eyebrows among those who had never witnessed engineering principles applied so counterintuitively. Tanks moving across 80-foot spans on structures that visibly twisted and flexed seemed to violate basic sense, even as the vehicles completed their crossings successfully. The roadways moved like living things, riding wave swells, ascending and descending many feet with tidal movement, while preserving structural integrity through Beckett's revolutionary joint designs. October revealed the initial hints that Beckett's adaptive thinking might surpass Hughes's massive approach, though neither man anticipated that Scottish weather would soon render their calculations irrelevant against forces testing both systems beyond their design parameters. October brought false confidence to Garliston Bay, as preliminary results suggested both remaining systems might function under actual combat situations. Hughes observed with quiet confidence as his hippo caissons demonstrated their load-bearing ability. The enormous concrete structures accepting 40-ton Churchill tanks without any deflection in their crocodile bridge spans. The rigid steel connections between caissons produced straight highway passages, enabling vehicles to maintain full speed while traveling from one artificial island to the next, precisely matching his theoretical predictions. Beckett's canvas system had already been rejected after proving unable to support anything beyond supply trucks. Its 7-ton maximum meant the first Sherman tank attempting passage would tear straight through the canvas into 20 feet of Scottish seawater. Beckett's flexible whale system continued mystifying observers who had never seen engineering principles deployed so unconventionally. The 80-foot spans twisted and undulated with wave motion like living creatures. Their torsional joints allowed each section to rotate independently while maintaining structural continuity via spherical bearings, accommodating movement in 3 dimensions all at once. Observing Churchill tanks traverse these snaking roadways demanded a complete rethinking of what constituted sufficient structural stability. The bridges moved constantly, rising and descending many feet with tidal forces. Yet the vehicles crossed without problems, while the flexible connections absorbed forces that would have destroyed rigid systems. The contrast between approaches became sharpest during intensive load testing in mid-October. Hughes's hippos accepted concentrated weights with the unmoving dignity of concrete pyramids, their vast mass distributing loads through internal steel frameworks designed to endure for centuries. Each caisson rested on the bay bottom like an artificial island, held steady by gravitational force and seafloor friction rather than relying on anchor systems that could potentially fail under extreme circumstances. The crocodile bridges spanning between these concrete monuments offered surfaces so stable that tank commanders could maintain ordinary driving speeds across gaps requiring careful maneuvering on conventional bridges. Beckett's system achieved equivalent load capacity through principles that seemed to violate common sense. His kite anchors, each weighing merely 3 tons, generated 30-ton holding power through hydrodynamic effects, multiplying their effective mass tenfold. The streamlined anchor design harnessed current flow to press angled surfaces against the sea floor, creating exponentially greater resistance than traditional deadweight approaches. The whale roadways themselves distributed tank loads through flexible connections, allowing stress to flow past concentration points rather than accumulating at rigid joints. By late October, the chiefs of staff seemed prepared to select Hughes's approach based purely on conceptual simplicity. Concrete caisson resting firmly on the seafloor corresponded with naval thinking, prioritizing established methods over innovative experiments. The Hippo system appeared like something the Royal Navy could comprehend and depend upon, massive and permanent, resisting forces through overwhelming strength rather than adaptive response. Hughes felt quiet vindication as senior officers nodded approvingly during demonstrations of his rigid bridge system, handling multiple Churchill tanks simultaneously without visible bending. Then Scotland's Atlantic weather shifted with the terrible suddenness that had terrified seafarers in these waters since ancient mariners first learned to dread the western storms. The low-pressure system forming west of the Hebrides on October 28th carried winds that had travelled 3,000 miles across open ocean, accumulating power from temperature differentials between Arctic air and the Gulf Stream's lingering warmth. When this weather bomb reached Garliston Bay, it drove 40-knot sustained winds with gusts surpassing 60 knots, pushing swells cresting at 15 feet, arriving with the mechanical rhythm of a battering ram assaulting castle walls. Within 6 hours of the storm's arrival, Hughes's Hippo caissons began failing in ways his calculations had never imagined. The massive concrete structures engineered to achieve stability through weight and bottom contact discovered that Scottish seafloors were not the solid foundations his theoretical assumptions had suggested. Sand and gravel beneath the caissons started scouring away under the hydraulic force of wave action, excavating voids that undermined the gravitational stability his entire system depended upon. Without firm bottom contact, the 7,700-ton concrete blocks shifted with every wave cycle. This movement placed bending loads on the rigid crocodile bridge connections designed purely for vertical stresses, never lateral forces. The steel joints connecting bridge spans to caissons represented the critical weakness in Hughes's philosophy of engineering through brute strength. Rigid connections that worked flawlessly under static loads started experiencing shear forces surpassing their design parameters as the massive concrete structures moved independently from their connecting bridges. One by one, the crocodile spans began separating from their anchor points as steel bolts sheared under stresses Hughes's calculations had deemed impossible. Beckett's canvas rolling roadway simply disintegrated during the storm. Its lightweight construction offered no resistance to winds that treated the canvas like a sail. Within hours, sections of roadway had torn from their moorings, washing ashore as twisted wreckage barely recognizable as the highway system that had seemed so promising during calm conditions. Beckett's whale system confronted identical 40-knot winds and 15-foot swells, destroying its competitors. Yet it responded through principles tested by millions of years of marine environmental evolution. The flexible spans twisted and flexed like kelp moving through storm currents, their torsional joints allowing each section to find equilibrium with wave forces rather than fighting a battle that could only conclude in structural failure. The pontoons supporting each whale span rose and descended with swells that would have overwhelmed rigid foundations, while the spherical bearings at connection points permitted three-dimensional movement that would have instantly destroyed conventional bridge joints. Most importantly, Beckett's kite anchors actually increased their holding power as storm conditions intensified. The streamlined anchor design used greater current velocities to create increased downward pressure on the seabed, producing a self-reinforcing system where greater storm energy produced proportionally stronger anchor capacity. While Hughes's massive caissons lost their grip on the shifting sea floor, Beckett's 3-ton anchors developed holding forces approaching 50 tons per unit under extreme circumstances. When dawn broke on November 1, 1943, only one harbour system remained intact and completely operational off the Scottish coast. Hughes stood among the debris of his life's work, observing concrete caissons costing hundreds of thousands of pounds, settling at distorted angles in Garliston Bay mud. their connecting bridges twisted into abstract sculptures by forces he had never imagined. The young royal engineer, whose flexible philosophy had seemed unconventional, suddenly found himself at the epicenter of the war's most critical technological choice. The aftermath left Hughes staring at the mathematical wreckage of everything he had believed regarding engineering. 2 years of calculations scattered across Garliston Bay in the form of concrete caissons tilted at impossible angles. Their rigid bridge connections twisted into abstract forms by forces never appearing in his stress equations. 15 years working with Owen Williams on architectural monuments intended to endure for centuries had taught him to regard concrete as a permanent material, achieving stability through mass and resistance. The storm proved permanence was an illusion when nature demonstrated the difference between theoretical loads and actual forces. Walking through his Hippocaïsan debris, Hughes faced the humbling truth that his expertise in building Wembley stadiums and soaring towers had not equipped him for structures requiring negotiation with the sea rather than simple domination. The concrete blocks that had seemed so monumentally stable in calm waters now resembled ancient ruins, their displacement revealing the fundamental flaw in his philosophy of engineering through overwhelming strength. The Scottish seafloor that his calculations had treated as solid foundation proved to be a shifting dynamic medium capable of undercutting 7,700-ton structures as effortlessly as wind reshapes sand dunes. Beckett's vindication carried the quiet satisfaction of a man whose unconventional thinking had been validated by forces beyond human control. The flexible harbor system that had seemed so unpredictable and fragile to conventional engineers had proven its worth through the harshest possible examination. 3 years of weekend work at Erith Yacht Club, experimenting with different anchor designs in Thames muddy waters, and observing how small craft moved through storm swells, had revealed solutions that centuries of naval tradition had somehow overlooked. The storm demonstrated that bending with force mattered far more than rigid resistance when facing power that could never be matched head-on. By November 1943, official military thinking had undergone a complete transformation as the leadership studied what they had witnessed off the Scottish coast. The quiet army engineer, whose unconventional ideas about flexible design had once drawn skepticism, suddenly found himself steering decisions that would affect the lives of 2 million Allied troops. Beckett's floating roadway system wasn't simply approved. It was expanded well beyond his original plan to 10 miles of flexible bridges, then stretched again to 16 miles, as strategists understood that invasion success rested entirely on the load capacity his innovative design could deliver. The manufacturing effort that followed eclipsed everything Britain had mobilized since war began. Over 2,300 kite anchors were ordered, each one built to Beckett's exact specifications to achieve the best possible performance in water. These weren't simple designs. Each anchor needed precision casting techniques that demanded more from British factories than they had ever attempted. Producing components that could hold back 30 tons of force while weighing only 3 tons through hydrodynamic principles that contradicted everything conventional anchor makers had assumed possible. Factories throughout Britain retooled their operations to produce parts for a harbour system that existed nowhere except in the mind of a 29-year-old engineer who had learned his trade by repairing equipment damaged in combat zones. The project would require 330,000 cubic yards of concrete, alongside 70,000 tons of steel, materials representing a massive chunk of Britain's total war production. 200,000 workers across nearly 150 construction sites would labor for half a year building components according to designs tested for just 4 weeks in Scottish conditions. Hughes watched his role transform from chief designer to supporting engineer, a painful shift as his concrete expertise became subordinate to Beckett's revolutionary approach. The new Phoenix caissons replaced his earlier Hippo design with smaller, more adaptable structures that could accommodate varying seabed conditions rather than demanding perfectly level foundations. 2 decades of architectural accomplishment seemed to dissolve when a 3-day storm rewrote the rules. Yet Hughes's concrete designs proved to be his greatest contribution to the invasion, though history would remember Beckett's name far more prominently. The concrete breakwaters sheltering Beckett's flexible roadways required the same mastery of reinforced concrete under extreme stress that had created Wembley Stadium. Hughes's ability to visualize massive structures bearing enormous weight became absolutely vital for harbour components that would endure not just Atlantic tempests, but relentless German artillery and bombing. These two engineers represented a fusion of opposing philosophies. One contributed massive permanence, the other adaptive movement. Separately, neither could have achieved what they accomplished together. Bruce White, the project coordinator whose First World War service had equipped him to handle impossible schedules during wartime, supervised an undertaking surpassing any military engineering venture in history. Organizing the manufacture of components across 146 separate locations, then coordinating transport and assembly along the Normandy coast, required administrative skill that strained Britain's capabilities to their absolute maximum. By April 1944, even skeptics who had dismissed Churchill's floating harbour concept as impractical had recognized the project's immense scope. Concrete Phoenix caissons, larger than destroyers themselves, crowded British river estuaries, waiting for tugboats to tow them across 100 miles of water they might not cross safely. Whale roadway sections occupied every suitable construction location, with flexible joints endlessly tested according to patterns Beckett had analysed from storm damage observations. The numbers revealed Britain's total commitment to an engineering solution proven viable for merely 7 months. £25 million, more than constructing an entire destroyer fleet, flowed into harbour components designed by two men not yet 70 between them. European liberation would hinge on whether concrete could journey 100 miles across the English Channel, withstand German destruction, and sustain 2 million soldiers advancing through France. June 6, 1944, would demonstrate whether every calculation and innovation born from those Scottish disaster ruins actually worked. The armada of concrete that crossed the Channel on D-Day represented history's boldest engineering wager. 132 tugboats strained against thick lines fastened to harbour components that had never faced actual combat conditions. Their engines labouring to move Phoenix caissons heavier than battleships across water patrolled by German submarines and watched by Luftwaffe pilots. Behind the massive concrete blocks came Beckett's whale roadway sections, resembling articulated creatures of the sea. Flexible joints permitted 80-foot spans to rise and fall with channel swells without the structural damage that rigid systems would have suffered across the 100-mile passage. The initial 10 days following D-Day confirmed every calculation emerging from those Scottish experiments. Both artificial harbours, Mulberry A off Omaha Beach and Mulberry B at Arromanches, began receiving cargo ships that would have required deep-water ports under normal circumstances. Phoenix caissons positioned themselves with hydraulic accuracy as internal flooding systems settled the concrete blocks onto the Norman seabed, creating breakwaters that converted exposed beaches into protected anchorages, capable of receiving Liberty ships carrying 5,000 tons of cargo each. Beckett's whale roadways connected the artificial islands with flexible spans that adjusted to tidal swings exceeding 12 feet, while maintaining surfaces capable of supporting 40-ton Churchill tanks racing to reinforce landing zones against German attacks. Hughes monitored the initial results from his London headquarters with the complicated feelings of someone whose professional defeat had contributed to history's most consequential engineering triumph. The Phoenix caissons performing flawlessly off Normandy embodied lessons from his failed Hippo design at Carisbrooke: smaller, more responsive structures accommodating variable seabed conditions rather than requiring perfect foundations. His concrete expertise had proven indispensable for creating breakwaters able to weather both Atlantic storms and concentrated German artillery bombardment. Yet recognition would flow primarily to Beckett's innovations. On June 19, 1944, meteorologists' deepest fears materialized. The same pressure system that had destroyed Hughes's rigid caissons in Scotland returned with full Atlantic force, unleashing 40-knot sustained winds across the Norman coast merely 13 days after invasion commenced. For 3 full days, both artificial harbours absorbed battering from waves reaching 15 feet, arriving with mechanical precision that stressed every joint, every anchor, every concrete block beyond design parameters established during calm water testing. Mulberry C. A off Omaha Beach suffered collapse within 36 hours. American engineers, doubting British anchor calculations and pressuring installation to accelerate, reduced the kite anchors per whale section below Beckett's specifications. The choice seemed sensible during calm periods when fewer anchors appeared sufficient for position maintenance. Storm conditions transformed this reasoning into catastrophe when forces multiplied anchor requirements by factors precisely predicted during Scottish trials. Insufficient anchors meant whale sections dragged failing anchor systems across the seabed, triggering cascading destruction, consuming $15 million of harbor equipment within 2 days. The Omaha failure vindicated every concern Beckett had raised about anchor requirements during planning. His kite anchors had been engineered to achieve exponentially greater holding capacity under storm conditions, using accelerated current velocity to intensify downward pressure against the seabed through hydrodynamic mechanics conventional deadweight anchors couldn't generate. American engineers who had dismissed these specifications as excessive British caution discovered that nature cared nothing for installation schedules or budget limitations. Mulberry B at Arromanches faced identical weather but survived through faithful execution of Beckett's anchor specifications and installation methods. The British harbour incorporated the complete set of kite anchors Scottish trials had demonstrated necessary, each 3-ton unit developing holding forces approaching 50 tons under extreme stress. Flexible whale roadways twisted and flexed like living organisms riding the tempest, with torsional joints permitting individual sections to achieve equilibrium, with wave forces rather than combating forces that assured failure. Hughes experienced the 3-day ordeal as hourly reports either confirming or destroying 2 years of professional accomplishment. Phoenix K. caissons sheltering Mulberry B displayed the concrete mastery that had constructed Wembley Stadium, their immense solidity providing breakwater defense that reduced outside wave heights from 15 feet to manageable 3 to 4 foot swells inside the artificial harbor. Success depended entirely on Beckett's flexible roadway system, which transformed protected water into a functioning port under conditions that would have closed traditional harbors. The storm aftermath illustrated the precision underlying Beckett's flexible approach. While Mulberry A scattered across the Norman seabed as concrete wreckage worth multiple destroyer fleets, Mulberry B emerged from identical weather fully intact and operational, resuming logistics supply determining Allied success or beach stalemate. Triumph and failure separated by anchor capacity and joint adaptability. Engineering minutiae, most observers considered trivial until nature demonstrated their absolute significance. By July 19, 1944, precisely 1 month following the Great Storm, Mulberry B had moved cargo volumes surpassing any occupied French port's capacity. 2.5 million soldiers traveled through the artificial harbor alongside 500,000 vehicles and 4 million tons of supplies, constituting European liberation's material foundation. Sherman tanks raced across Beckett's flexible roadways at speeds impossible on conventional docks, while Liberty ships unloaded directly onto whale sections rising and falling with tides without disrupting operations. Phoenix concrete blocks proved their importance through less conspicuous but equally essential service. Hughes's Phoenix caissons sustained functional harbor basins under weather conditions, closing ports from Cherbourg to Le Havre, supplying sheltered water where Beckett's flexible roadways revealed their revolutionary performance capabilities. Strength combined with adaptability had created an engineering system surpassing any conventionally built harbor facility. German military leadership recognized the Mulberry Harbor's strategic significance through concentrated artillery bombardment and aerial bombing testing, every dimension of Hughes's concrete engineering. Phoenix caissons withstood direct strikes from 88mm guns and 250-kilogram bombs while maintaining structural soundness, proving reinforced concrete could survive oceanic violence plus explosive force German defenders unleashed against the artificial ports. During Nuremberg proceedings, Albert Speer acknowledged that Mulberry Harbor had destroyed 2 years of Atlantic Wall construction through what he termed simple genius expressed magnificently. Phoenix caissons remain visible at low tide off Arromanches today, concrete reminders of the engineering transformation making D-Day sustainable. Massive blocks that crossed 100 miles through hostile waters, endured Atlantic storms, and held position under enemy fire demonstrated that the impossible was merely something not yet attempted.